guys ready? Yeah. Okay, great. You're ready. So today, as a speaker, we have Professor Hamsa Balakrishnan. Hamsa is Associate Department Head in MIT's Aeronautics and Astronautics Department, where I'm from as well. Hamsa is also the Head of Transportation Initiative at MIT. And she's doing all kinds of cool work on control and coordination for all kinds of infrastructure. But she mainly focuses on air transportation systems. And today she's going to tell us about lean, green, and flying machines. Let's welcome Hamsa.
Thank you. I'm going to give a little bit of a broad overview on why I love air traffic problems. I think, hopefully I'll share that excitement with some of you as well. And, feel free to sort of stop. I'm going to leave enough time at the end for us to, have a discussion, but feel free to, stop me if something is not clear, right, along the way. So, it's hard to argue with the fact that air travel, air transportation really has become a driver of global travel and global commerce, right? So just in terms of the scale of it, if we think about commercial, so airline passengers, there's about 4.5 billion enplanements a year. So this is somebody getting on board a flight and beginning a journey, right? And commercially, there are about 50 million flights worldwide. A lot of this tends to be concentrated currently in the US and Europe, but then the biggest rate of growth, is happening in places where, like Asia, so India and China, where there's a rapid development of new airports and there's a lot of demand for travel as well. But as demand grows, one of the things, of course, is the pain associated, right? As more and more, if you operate more and more traffic, you have more and more congestion and more delays. And there's a real economic consequence here. So in the US, for example, it's estimated that delays alone cost about $30 to $40 billion a year to the US economy. And there's also something we really care about, namely the environmental impact, right? So these delays are inefficient from the point of view of our time, the passenger's time, but the delays lead to an excess consumption of fuel as well. So it's about 740 million gallons of fuel are wasted because of delays. And there's also, environmental impact in terms of CO2 emissions, which is about, 7 million metric tons of CO2. But of course, as the demand has been growing, it's been pretty steady. So commercial air travel demand grows worldwide at about 6% a year. It's been pretty steady over the past, couple of decades. But you also realize that as this grows, you need to scale up the system, right? You need to be able to meet this excess demand. And there's two things that are really changing as we think about, transforming these systems. So there are efforts in terms of next generation air transportation systems. How do we meet this growth in demand? And it's clear that there's two trends that are going to happen. So you're going to have an increase in the levels of autonomy, right? And I know that several of you are working on this, so it'll be cool to talk about it later. Much like any other mode of transportation, or in fact any other engineered infrastructure, you're going to have more decision making that's on board the vehicle or at the system level. And also you need automation. And by that I mean you have human decision makers, right, like the air traffic controllers or the pilots, but as there's more and more traffic and the skies get busier, you need support, decision support for them, right? And so that's needed. And in terms of just autonomous traffic, there's demand that we expect in terms of unmanned aircraft, so drones, for a lot of societal good applications. But there's also things that we think are going to are projected to happen, like urban air mobility. So think about rideshare, on-demand rideshare, but with in urban areas, but you don't go on the road, right? So you don't deal with the LA freeway anymore because you can take an autonomous helicopter, essentially, to go from one place to the other. So this is what we're trying to do, where a lot of the work we do tries to scale up and transform the system so that we can meet these new forms of demand. It's also sort of helpful to remember that this is happening everywhere in the world, though a lot of what I'll talk about will be US-centric. So this movie is almost 15 years old. But it sort of shows where, how traffic flows work around the world. So the lighter regions are typically where there's daylight. And you see that it's a 24 hours a day, there's traffic somewhere in the world. As I said, this is about 15 years ago because there's a lot more traffic in India and China now than there was 15 years ago. But you can see that US and Europe, as it's daytime, they're going to get much busier. And also you can see the streams of traffic. So twice a day, the direction of these streams change. So as flights go from Europe to the US, they reach here around the afternoon. And then when it's evening in the US, you're going to see a lot of, in the East Coast, you're going to see a lot of flights going the other direction so that you can get to Europe in time for your 9 a.m. meetings the next morning, and so on. But you can also see that there are pretty congested skies already. Towards the end of this, I'll show you what we expect and how we would try to manage these skies in 2030, right, when you have 3 times this amount of traffic in the air efficiently. So where does a lot of the work that I do fall in? So as Satash mentioned, I'm in the Aero department. My work deals a lot with the algorithmic side, so building control and optimization algorithms for this. And in particular, we really care about practical algorithms, right? By practical, we mean things that we can experiment with, we can implement, and are realistic, things that we can actually deploy. What do we want to build these algorithms for? Well, overall, it's very easy to say, I want a more efficient system, right? I have some resources in terms of how much airspace I have or where my airports are, so I want to use them as efficiently as possible. I want to be as robust as possible, right? So one of the things that we'll see over the course of this is the system is at a point where if you have a bad weather day in New York, you're going to end up having delays pretty much everywhere, right? So you want to be a little less fragile and more robust to disturbances that happen in the system, and you want to do this while maintaining, the levels of safety that aviation has historically seen. And what makes it hard to do in practice when we start thinking about how do you, convert this to mathematical models that you can actually, or abstractions that you can make decisions over, or automate decisions over. There are lots of difficult things, but there are 3 main challenges that I will focus on. The first is there's a lot of uncertainty, right? So no matter what, there is some uncertainty associated in terms of the weather conditions or in terms of what is likely to happen. There might be random failures for mechanical reasons. There could be, not everything is deterministic in this world, right? There are random perturbations that happen. The second is, it is still, we're nowhere near the stage where there are no humans involved and everything is automated and everything's perfect, right? So it is very much we're building and trying to, get more intelligence into systems which inherently have human operators. And even when there will not be, if you have a higher level of autonomy in the system, you're going to have human decision makers, right? Ultimately, you're going to have somebody who cares about, a human passenger or a human airline executive who's trying to make these decisions, has their objectives in mind and their, all the interactions right now with air traffic controllers, there are humans who are involved there as well. And then the third part of it is competition, right? So you want to do this in an environment where you have competing interests, where the airlines, you want airlines to be, or aircraft operators, your drone operators or your, rideshare operators to actually be able to have a viable business out of it, which means they are competing. And so a lot of what we want to do, we want to be able to do in a competitive environment. So we want to build algorithms that are going to be able to handle competitive environments. So how do we go about doing this? Well, our approach overall at a very high level is the following. So there's an increasing amount of real-world data. So we're going to try to use as much operational data as possible in order to build our abstractions and our models. And in particular, because we have these human operators and human stakeholders, it's actually important to have reasonably simple in the sense of physically interpretable models, right? So if you're going to build a decision support tool for an air traffic controller or a pilot, you want it to be something that they would trust and something that they think is a reasonable thing for the system to be doing. And so you need to be able to explain why a particular decision is made, right? So they have to be interpretable in that way. And then because we have this growth in demand that we expect, we want the algorithms themselves to be scalable, right? So they need to be the scale as the amount of traffic grows. And ultimately, what our belief is really that this sort of building these algorithms you can implement and using them to have decision support is going to be the way in which we can transform the system. And it's important for us to realize that there are sort of three elements in everything that we do. One is the cyber element, right? So we're building automation and intelligence to make decisions, so it's important to think about how that works. The second is the physical element, because everything is aircraft. So there's things like what an aircraft can actually do that we need to think about, and what the physical constraints of airport layout is going to be, and so on. And the third is that the human element, where the humans are the ones making the decisions. So all three of these are going to be important. And today, sir, I'm going to focus on three things, right? So I'll give three little challenges and talk about research in three areas. The first is work that we do at a very, think about you have this large network with, the flows that we saw. I'm going to talk about how we deal, how we can go about looking at efficiency at the level of an airport, right, which is a node in that large network. So that's really looking at congestion control, but in the context of, traffic on the ground at an airport. The second is going to be sort of moving from that to trying to decrease delays, right? So mitigating delays and improving efficiency, which is going to look at some challenges in very large-scale optimization, where we're trying to optimize everybody's trajectory at the same time, understanding what needs to be done. And then the third is at an abstraction level, thinking about how all of these systems are connected, and so trying to understand the dynamics of these systems. So how delays propagate, which is very similar to questions that you might ask on infection. So how epidemics propagate, or how rumors propagate, right? So there's similarities to many other problems that we care about. Okay, so why do I care about the first thing? So here is something that's pretty remarkable about airport congestion. About 20% of delays at major US airports happen not because there's bad weather, right? We complain a lot about weather. They actually happen because there's so much traffic demand that there's actually good weather, and you have just too much demand, right? Traffic. So you don't have the ability to meet that. So this is, I'm guessing most of you have either a lot of you have either flown into Boston, or will fly out of Boston, or have been to the airport. The green aircraft, so this is a typical summer day. The green aircraft are aircraft that are lining up to take off from this runway. The red aircraft are arrivals that are landing on this runway, and then a few of them are landing on this runway as well. Occasionally, you have an aircraft that lands and takes a wrong turn, and then you end up in this long line. This happens at many busy airports, so it happens at so many airports, and then you got to pretty much wait, right? So you can't get out of line because you got to stay on a taxiway. So you wait till it's your turn to use the runway, and then you come back to your gate, right? And at airports like Philadelphia, that's sort of a small, unintentional action on the point of, a pilot, or for something like that will be 45 minutes, right? You come back to the gate, you have to wait. Maybe you don't have a gate, you end up having it, and then so you have delays that go up. And this form of airport congestion we really care about because it increases taxi times, so delays, but also fuel burn and emissions. And so we'd like to sort of think about how often does this happen, can we tell it's going to happen, and then can we build intelligence so that we can actually avoid cases where aircraft are basically lining up and you have 30, 40 aircraft lining up to wait, going nowhere, right? So as I said, this happens at a lot of airports. So one thing that we can ask is, how do we just look at data very quickly and tell when this is happening, how often this is happening? So we build, a lot of our models are going to look at abstractions as queues, right? So at these airports, what aircraft typically queue up, there's congestion near a runway, like we saw. They can't take off because, you can only operate an aircraft every 30 seconds off the runway, can take off the runway, or an aircraft can only take off typically once a minute or something like that. Right, so this is looking at John F. Kennedy Airport in New York, and this is from 2009. And so an easy sort of way to just think about the problem is we plot the number of aircraft. So the x-axis has the number of active departures on the ground, right? So how many aircraft have already left their gates, turned their engines on, but have not taken off yet. And then the vertical axis is the rate at which they're actually taking off, right, leaving the airport surface. So what we see is that initially, if there's nobody else on the ground, I leave, I push back, I taxi to the runway, and then I take off whenever I get there, right? So initially everybody pushes back, and then you keep taking off. But there's some capacity limit to what the airport can possibly do, and the moment you hit that, you end up spending time just lining up and waiting. And that number here is somewhere around 27. Actually, the record that I've heard of at JFK is there was a day in 2008 when there were 80 aircraft in line for departure. Right? And so our basic thing when we go in here is, at some point somebody must have said, if I'm the 70th aircraft that's pushed back and I have 69 aircraft in front of me, then it's probably going to take me another hour to take off, right? So I might as well wait here with my engines off and leave later, and I'll still leave, get there at the same time. So, and this happens quite often. So at JFK, in this year, for example, about a third of aircraft actually would depart when the airport was saturated like this. And even under good weather conditions, your average taxi out time, right? So there's no weather issue. Your average, how long does it take for you to get from your gate to the runway and get from the gate to take off? It's about an hour, when it should be taking you, less than 20 minutes, right? So that's time that's spent basically sitting there with your engines on, wasting fuel, and polluting the environment. So when we see this, the idea now is, okay, let's build an algorithm which will tell us how we can control this and avoid this problem, right? And what do we care about? And then what is going to be difficult? What do we really need to be careful about when we do this? So this is a very basic idea, right? So aircraft are leaving their gates. They're going through the taxiways. They're waiting in queue for, to be able to take off at the runway. And then they're taking off. What we want to do is we want to avoid the case where you have, too many aircraft and they're just going to wait and waste time at the runway with their engines on. But at the same time, if I go super, to the other extreme where I say I'm only going to let one aircraft leave every 15 minutes, then I'm only going to have an aircraft take off every 15 minutes. And that's going to be bad because I'm wasting, I'm adding unnecessary delay. Right? So what we want to do is build algorithms that can regulate our pushbacks in order to keep the runway busy all the time. There should always be a few people few aircraft ready to take off, but it has to be a few. It shouldn't be, a crazy high number. So the challenges now that we'll have to work out are firstly, okay, how do you actually design a control strategy that, that's going to achieve these objectives? The second, of course, is that you want to have a control strategy that you can implement today. Right? So the thing you're going to have to, I said you want practical algorithms. So you want an algorithm where you can give decisions based on input that you actually have at an airport and that you can actually implement with human air traffic controllers, right? Because we want to do this today, not 40 years from now. So that's basically the idea. And at a very high level, what do we do? What we have are to design the first question, how do you design a control strategy? Well, we can use dynamic programming, so it's an optimization technique, to look at essentially two things. So we want to be able to look at the current state of the airport, right? How many people are out there? How many how many aircraft are going to be ready to push back? Sorry, I think aircraft are people, right? Sorry. How many aircraft are already, about to, ready to take off, how many of them are making their way to the runways and so on, and use that to predict what is likely to happen over the next 15 minutes or the next half hour, right? And then use that to make a decision optimally on how many more aircraft do I release in order to keep the runway busy, but not too busy, right? Busy enough and not too busy. And that's really the idea. And so you essentially build these models, so these predictive models using operational data. Historically, given weather conditions, given everything else, like the plot that I showed earlier, those saturation plots, we can use that to predict what is likely to happen, and then we use that in order to come up with an action on what should we be doing. So when we so we're going to try this, right? So we implemented this at Boston Logan Airport. Our first idea was the following, which is like the simplest thing we can think of. Somebody comes and says, well, my problem is I have too many aircraft on the ground that are waiting in line. So I say, fine. So I'm going to have this policy where I'm going to decide what the right number of aircraft to have on the ground is. And it seems to be about 27 there, right, based on that earlier thing at JFK. So maybe it's 20 at Boston Logan. So every time I look out of the window, or I look at any data set and see there are 21 aircraft on the ground, I'm going to wait. I'm going to tell the controller, don't release any more. I'm going to then wait till somebody, an aircraft takes off. And then now that I have fewer than 20, I will release another aircraft, right? So I'm going to do this sort of on-off policy. So we went there and we told the FAA, air traffic controllers, hey, we have this beautiful policy. We think it's going to work. They came back and said, that's not going to work because what you're suggesting is you're going to be standing in the tower, and every 2 minutes or every minute randomly, you're going to tap on an air traffic controller's back and tell them that, hey, don't release the next aircraft, hold on, don't, and so on. And that's extremely distracting for somebody who's actually doing an important job, right, maintaining safety. So what they said instead is, tell us something to do. So we don't want this sort of very distracted policy. Give us an algorithm which can do the same thing, achieve the same objectives, but instead tell us, every 15 minutes, tell us roughly you need to be releasing at this rate, right? So release an aircraft every 2 minutes, or release an aircraft every 2 aircraft every 3 minutes or something like that. And then you can come back every 15 minutes and tell us how to change that, but you can't, have that policy. So what we finally, essentially come up with is this is what an optimal policy might look like, where what the algorithm is doing, what the automation is doing is it's looking at how many aircraft are potentially in the departure queue. So they're already waiting near the runway. How many aircraft have left the gates but are still moving to the runway, using the predictions and essentially coming up with these sort of strategies which says, if you're somewhere, if I'm out here where I have 20-something, 23 aircraft on the ground already, then you can just stop things for the next 15 minutes because you're good for the next 15 minutes and even longer. On the other hand, if I'm out here where I don't have anybody on the ground, you want to keep pushing, and then in between you have this gradual thing where you're actually looking automatically and giving this guidance, right? And you can update this every 15 minutes. So, okay, so now we have the first two things where we can use the dynamic program, the algorithm to come up with what these policies might be under. Under the hood here is a prediction of what the rate is likely to be, what the uncertainty is, and so on. But you can use that to come up with this policy. And we know we can't keep telling controllers yes, no, but we'll give it to them in 15-minute intervals. Then the next question is, how do you actually tell them that this is the rate, right? And so we went super low-tech initially, where the first year we did this in 2010, we had color-coded cards, right? So this is like simple, right? These things are just these 5-inch by 7.5-inch cards. So this is sort of how the card is located at a controller's position. And we have we sort of round up those rates to these and give them one of these cards, right? And so we don't talk to them. There's somebody at the back of the room, so it's a student, and we go there and then we swap that out, right? The next year, we said, okay, but we can do this and actually give extra guidance as well. So we went to way more expensive cards, right? So you have a tablet interface where all of this is completely automated now. So this was actually developed by a high school student who was working in the lab. So the idea is two things you can do. One is, at a very basic level, this is what the supervisor, the coordinator is seeing at the back. He or she is making sure, again, that this is reasonable, right? Which is important because they sort of need to understand not just the final decision, but also what is going in, right? It's important that they have trust in it. And then out here, they actually have what the controller sees. And then one thing we noticed here is once you have this sort of display, they use it to actually bookkeep other things, right? There's an awful lot of things right now that happen with human controllers on, making notations on, a sheet of paper, which is forever lost to posterity. So, you go back and you ask, why did somebody do something, and you have no idea, right? So, whereas this is an easier way of actually keeping track of decisions that get made. And then, of course, the next question was, is this kind of thing actually going to help with our original problem, right? Namely that of congestion. And so, I'm going to show a couple of days and what happens when we do this. So this is, as I said, this was a few years ago. So this was, most of this is in summer in 2011. And so this, so there are three things here. I'll just sort of walk through these. So the first one is showing for each 15-minute period when we're actually there and we're sort of metering traffic, right? We're regulating these traffic flows. The orange bars are showing how many aircraft, how many pilots actually called and said they were ready to push, and the green show how many were actually allowed to push, right? They were cleared to push. And so during, initially and the blue line here is showing what is called work in process, which is basically how many aircraft are currently on the surface active but have not taken off. And so you notice that initially as congestion builds up, you have more and more aircraft on the ground, but then at some point you realize, okay, we're congested, so we should start holding a few of these aircraft back. But then you want to hold them back so that you're still not starving the runway, and you want to keep that going. And then the other thing that we always care about is when you're predicting, are your predictions actually good? So at any time, we keep a running tally of are we within. So we're making these predictions, and we're also predicting it with how confident we are, right? What's the uncertainty bound on that? And so you can typically predict what the airport is going to be doing to within a couple of aircraft, which is good. And then ultimately, what do you actually gain? Well, what you want to see is that as congestion builds up, and the green bar here is how, the average taxi out time, you don't want that average taxi out time to keep growing. You want to be trading off that taxi out time when aircraft have their engines on for time that they're spending with their engines off at that gate, right? So you want to have that fair thing where it's going to take me 15 minutes from now until when I take off, but then I'm only going to spend 10 of those minutes with my engines on. I'm going to spend 5 of those at my gate with the engines off, so I don't have to, burn fuel. And then, what do we want to see here? Well, what I want to see here when you visualize this is not have a queue of 40, 50 aircraft. So this is the same day as time progresses. And so I want to still keep a few, right, because there's enough uncertainty in this. And it turns out that about 4 or 5 aircraft is the sweet spot that you want to keep in order to keep pressure on the runway. But at the same time, at this point, we're holding about 20 aircraft back here, right, because we realize that we don't need to let them all go in order to keep this much pressure on the runway. So we don't want to see anything weird happening. There's another one, which I realize the date is off on this, so I apologize for that. So this is actually in 2010. And the difference here was this is a day when there's construction going on in this white, there. This is a day when there's construction going on here. So at this, in 2010, when we went in and did this, what aircraft would have to do is they would leave the gates here. They would still be taking off in this runway, but they couldn't go down this path. So they would go here, wait to cross this runway, and then go and then take off here. So we're going to start the video with looking at the flight tracks before we start metering, and then I'll tell you when we start metering, right? And then we'll see how things change. So initially, we noticed that there's a really long queue here, but there's also a longer queue that gets formed here. And then just about in another few seconds, so around 7, we start metering. And what we're going to do is now hold aircraft back here so that the sort of the size of the queue we see here is much smaller, and we have a flow that keeps going. Right? We're maintaining pressure on the runway, but at the same time, not too many. I want to play that again because when we, the first time we did this in 2010, one of the supervisors came and said there's another change that's happened in how the controllers are working this, right? So the way it works at an airport is there's an air traffic controller who's responsible for this runway. So he or she has to give clearance for each of these aircraft to take off. they also have to give clearance for these aircraft to cross that runway, right? So they're there to make sure that nobody is crossing at the same time that someone is trying to take off. So initially, when we're not metering and they actually have two queues they're serving, this really long queue and another really long queue, what they tend to do is pretty much let people cross after each aircraft, after every departure, which is extremely inefficient. But you can imagine that, and then when we start metering, they actually let an aircraft take off, let a few aircraft take off, group the crossings, and then let them go together. But that's human psychology, right? So if I have two queues and they're both long and they're both pushing me all the time, the natural thing I'm going to do is to serve one, even if it's extremely inefficient, because it's like, I'm constantly doing two different things. On the other hand, if we sort of pace things better, then they start thinking about efficiency, right? They can think about, okay, I'm going to wait till a heavy aircraft takes off, and then I have a natural gap before the next other aircraft can take off, so I'm going to let 2 or 3 aircraft cross together. So that's actually an interesting thing in terms of flows. So this is broadly, something in this. So, what can one do? What has this done? Well, so we've shown, firstly, this was one of the first, this is the first time when you could show that this sort of departure metering, you can actually build algorithms that you can use today in order to make things better, and they can be reasonably lightweight and yet very effective. So we sort of demoed this across 15 days, right? 15 periods of about 3 to 4 hours each time. You don't hold aircraft back very much, right? So it's not like you're adding half an hour of delay. All you do is hold typically, an average aircraft back maybe an extra 5 minutes. But then in terms of fuel burn savings and in terms of emission savings, you get a lot of benefit from, because there is so much wastage that happens just because people are lining up, that all you have to do is, slow things down a little bit. The second thing that was really nice for us is I talked earlier about how it's important to realize that there are competitive interests here. So, issues of fairness are really important, right? It's important for the airlines also for us to be able to show that the algorithms themselves will be fair, and that if there's an airline that gets a minute of being held at the gate, it's going to see a minute of savings, as opposed to, I'm an airline, I get all the delay of the gate hold, and somebody else gets all the savings, or, vice versa. So you can show that there's actually a fair distribution. And then where we've gone since then is supporting the FAA in their departure metering, which is going to become standard at all major airports. So trying to understand, how do you do this when there are more complex airports? How do you adapt algorithms quickly to different types of surroundings and different levels of uncertainty and so on. So that's sort of something that we can do fairly easily in demonstrating how things can get better through using intelligence at a sort of very local airport level. The second thing, of course, we care about is how does this now extend to everywhere, right? So I'm going to talk a little bit about large-scale optimization, so going from an airport to doing this the airspace and everything else. And in particular, we really care at the large scale about a couple of things. So weather is a huge issue. So I'm going to play this movie. So let me just set it up. So these are traffic flows into the New York, Philadelphia area. Each red dot is going to be an aircraft, and a white line behind it is 5 minutes of history, right? So where the aircraft has been over the 5 minutes. And these are storm cells, right? So the green is, some weather, but the red and the yellow ones are really bad weather that you can't fly through. So this is a thunderstorm in summer. There. So this is weather that's moving into the New York area. So initially, everybody's going fine. Weather moves into, from the north towards the airport. You realize that these flows can't get in, so you start having these holding patterns formed, right? I mean, this is far away, right? So you have holding patterns being formed halfway across the country. The weather then moves south, and then you have holding patterns being formed in Florida because of weather that's happening in New York. And that's sort of how the system responds now, where if you don't plan a little bit strategically that there's going to be a storm that's coming and think about how you're going to pace your flows, everybody shows up at the same time. You don't have enough capacity. So what happens is the airport realizes that the airport tower says, well, we're not going to be able to, have as many aircraft land as are showing up right now. So hold on. So they tell the first airspace region, right, sector next to them, hold on. And so then that sector says, well, I have all the people I can hold here. So they tell the next person, hold on. And then they tell the next person, hold on. And then they have this cascade of delays through the system. And airborne delays, this is just people burning fuel in the air, right, at 30,000 feet. So that's really bad. So we sort of want to deal with this issue. And so this is really a congestion issue. So we talked about congestion on the ground, where a large part of it, as I mentioned earlier, was just too much demand and not enough supply, right? Not enough capacity. But congestion happens every time when you need more of something than you actually have. So it happens either when you have a reduction in capacity, which happens because of weather, for example, or it happens when you've just overscheduled, which is what we had done in the first thing. And this sort of delays, as I said, have a real impact, and this is true in any congestion system, both in the US and in Europe. It's estimated, these are expensive things. And what algorithmically, there's a problem which we tried to solve operationally called air traffic flow management, which is essentially, I want to be able to allocate these resources, right? How many aircraft are going to land at this airport at some time? How many are going to pass through this region of airspace at some time? All of which is going to impact our trajectories in order to sort of minimize costs, right? Mitigate delays, mitigate disruption, and so on. And then there's one other thing that actually makes this sort of thing hard, not just the cascade of delays from, in the airspace, but I'm going to show another movie, which is looking at delays on a bad weather day, right? So this is a playback of data. And so the way to read this, hopefully you can see colors. So I should point out firstly, the aircraft are not to scale, right? The grayer aircraft, and so this is a day when there's weather pretty much in the Chicago area, right, which is around here. And aircraft are going to turn yellow if they've been delayed at least 15 minutes, and then they're going to turn red if they've been delayed by at least an hour, right? And so this is weather in the morning in Chicago, basically. So initially, you see that the flights that are leaving Chicago are, turning yellow, and most of this ends up being in the East Coast. But as the day progresses, right, the problem doesn't stay here. The problem ends up in other places. So you have flights from Seattle to San Francisco or Seattle to LA that are going to get delayed by an hour. And the reason for this, of course, is that the aircraft doesn't stay there. So the flight is an hour delayed getting out of Chicago. The aircraft goes to Seattle. It's an hour delayed getting into Seattle. Maybe you have another half an hour before the next flight. Maybe the airline has said, okay, it might be late, and so schedule 15 minutes. You're still going to be about 45 minutes late leaving Seattle on your way to LA and so on. So these delays spread. And so when we think about managing these flows, so I want to talk about, we want to optimize these flows. We should also think about, well, we're optimizing these flows, but this is what's happening, 10 years ago or now. We are expecting way more demand, right? So the projections in terms of unmanned aircraft or even urban air mobility, we're expecting something like, 100-fold increase in congestion near some airports, right, major airports. So this is going to be pretty congested. There's a lot of interest, right, venture interest in this. And actually, how many of you have a drone? Yeah, this is a room which is pretty, but that's exactly the thing. So just in terms of sheer numbers, there's about 220,000 registered commercial aircraft in the world, right? DJI alone sells about that many a month, right? So there's an order of magnitude scale in how much demand we expect in some of this. And the challenge really is, in some regions it's going to interact with manned traffic, some regions it's not. How do you do all of that? So the kind of challenges we deal with, so one is just capacity. You have these limits on how many aircraft you can have in some region of airspace. There might be regions of airspace where you only want to have unmanned traffic. There are regions of airspace where you don't want unmanned traffic to go, right? So you want to be able to block that kind of thing off, and you also want to have your airport rates and everything else that can change very rapidly be satisfied. And the second is that problem that I showed in the video where a delay in Chicago ends up everywhere. It turns out that in the US, only about 6% of aircraft actually fly one flight a day and then they're done for the day. So, the average aircraft flies somewhere between 4 and 6 flights a day, right? So what this means from optimizing and managing traffic is that if I decide that it's the right decision for me to massively delay a flight now, right? Because it's the optimal thing for me to do in the next 3 hours, and I don't realize that that flight has 4 other flights. That decision now is going to impact every decision, every flight that aircraft is going to operate later, right? So it sort of poses a challenge in terms of how we, optimizing the system as well. And then, of course, it results in delay propagation. And both in the US and Europe, about 40% of flight delays occur because the previous aircraft, the aircraft has shown up late, right? So we've all been at the airport and the aircraft is not there, right? We're there, the aircraft's not there. So that's a key thing. So in terms of optimization, it's a very at a high level. What we want to be able to do when we're managing these flows is, again, think about what do we want to optimize? Well, we want to maximize some notion of benefit, right? It might be minimizing delays. It might be maximizing how much, how many passengers we carry. So there are all sorts of different objectives. We want to do it in a way where airlines can be flexible with their decisions. So you want to be able to do this fast. And you want to satisfy your constraints, which are make sure that you don't have too many aircraft showing up to land at an airport if you don't have capacity. Make sure that you don't have too many aircraft in the same area. Make sure that you actually consider what that aircraft is going to do later. Obey the laws of physics, right? They can't fly infinitely fast. They don't have an infinite amount of fuel, things like that. And there's only a limited number of things we can do. We can hold aircraft on the ground. We can hold aircraft in the air. We can make them fly a slightly different route by changing their speeds, and we can hold them so long that the airline's going to cancel the flight, right? So that's all we can do. And then we want to do this, as I said, for tomorrow's air traffic management challenges, which really, as I alluded to earlier, is the idea of autonomy, right? So you want to do this with having aircraft that are manned, unmanned, doing various different things. So I actually love this. I want to see this, right? So you want an autonomous flight crossing of the Atlantic. When do we think this is going to happen? Soon, yeah. You bet. Right. So that's a New York Times headline from 1947, right? So we've known, the challenge really is at some level we've known how to fly, fly there. There are several remarkable things. I recommend this from the New York Times archives, this article. Firstly, there were civilians on board. So, people had a lot of faith in automation. It was a mechanical brain, right? But, in terms of the code, they saw both drone warfare and Amazon Prime, right, coming here, which is in peaceful time, you're going to use this as cargo operations are going to become fully autonomous, right? But again, we hope to see that soon. The reality is we don't know how to do this, constantly with no exception and do it in a congested airspace, right? You can do this if you shut everything else down and you are willing if that's your thing. So what we can do, however, with the optimization models is actually show that you can optimize these skies later. And I'm going to just end a little bit with this piece with showing what kind of things we can do now, right? What do we have the ability to do in terms of integration? So, this is just a computational thing on how would you do this. So you have a demand set for 2030 from the FAA, which has, so we now have about 25 to 30,000 flights a day. They expect that there's going to be closer to 50,000 flights, commercial aircraft flights. They have some new runways, capacity improvements coming up, so we look at that. And then we get a sort of unmanned data set here. They don't have urban air mobility, but they have lots of drones with, varying range of altitudes, a lot of them, and I'll show a couple are doing, sort of surveillance, aquaculture missions, and then you can run this very quickly. So what we can do is essentially optimize that kind of, going to 77,000 flights a day, looking at a trajectory once a minute and do it in under 4 minutes, right? Because you essentially distribute this and solve this on the cloud. And then you can do it even faster if you're doing, every 6 to 8 hours and you change things, you can do it even faster. So what does that look like? What do we think the skies are going to look like in 2030? Or what does the FAA think the skies are going to look like in 2030? Okay, so there are going to be two kinds of aircraft. The red aircraft are going to be unmanned, and the blue aircraft are going to be manned. So you can see already that there's a difference in what they're likely to be doing. We are in essentially optimizing. So aircraft are sort of saying, here's roughly what I want to do. You're looking at resource constraints, and then you're optimizing what they are. So you see out here, there's a fair amount of, of UAV missions that they expect out here. But also here at a range of altitudes, right? Depending on whether you're doing communications missions or photography missions, you essentially have everything from 100 feet to 60,000 feet. But the reality of this is we actually now have the, it used to be that we would say we can't optimize because we don't have the ability to do it. It's an intractable problem, right? But the reality now is it's no longer an intractable problem, and we can do this with mixed demand, right? So you can now start thinking about issues of how do you integrate, because we can actually optimize and communicate. Yeah. So, and then the last thing, of course, and I'm not going to spend any time doing this, is thinking at the propagation level of how things propagate in a very large network across scale. And we care about this because, as I said earlier, we have a lot of instances where whether it's irrespective of whether it's weather, like thunderstorms, or it's a power outage, or it's a fire somewhere, you end up with one problem going everywhere. So just in terms of scale, the power outage in Atlanta here, this was August 2016, it lasted about an hour, right? The impact of it, the effects of it lasted about 3 days. There were a few thousand flights that were canceled, and it was a $150 million impact for essentially a short power outage in one airline. Right? So these are things that very rapidly spread. And the reason we really care about understanding these large disruptions are that we also see that they have become much more frequent. So this is just looking over the past decade on how many days in a season, so a 3-month period, do you actually see more than 1,000 cancellations in the US. And it used to be it would happen primarily, the bad, snowstorm or bad winter would mean we would have a few days when we had massive cancellations. Now it happens all the time, right? And it's not just winter, because it happens because of hurricanes. It happens because there's so much demand that those disruptions end up being massive everywhere. So we can think about essentially methodologies. We work on more graphical models and methods based on graphical network analysis to characterize these large disruptions so that we can help an airline understand what do you do when it's a hurricane versus a power outage versus a radar outage versus a snowstorm, right? How do you recover from this? And really the reason why we care about it is that there are lots of interdependencies, right? Airlines need power. You need the airport to be accessible. So traditionally, when there's a snowstorm, you would clear out the airport runways, right? And so this is Atlanta Airport a few years ago, 2 hours after it starts snowing, right? But then they ended up having massive cancellations because this is what the outside of the airport looked like. So it doesn't matter if I clear out my runways, if I can't get my crews in and I can't get my passengers in, I'm still going to have disruptions. So we really need to be able to understand more broadly what's happening. Of course, I should also point out this was 2 inches of snow, which if you're from the Northeast, we'd laugh, but it's still an issue. And then it's also an opportunity because there are parts of the world where if you have constraints, you should be thinking about, should we be using other modes of transportation? Should we be using high-speed rail? Is that a better way of using this than this sort of thing? So I'm going to stop there, and we can spend some time chatting about all of this. Really, I think thinking about how do we build intelligence into these systems can really make a difference. And there are lots of exciting problems in this, right, that we can work on. So thank you.
Few questions. Any questions?
Yep.
So for your 2010 to 2011.
Sorry. So I think it's very hard to draw a distinction between those two. And I think it is, so I consider myself both, right? Because you cannot build algorithms for domains without having an understanding of how that domain works, right? So I think it is, when I say we want practical algorithms, I think it's both. So I come from background in both, and I think that's important, and I think that's true of so many of us in, today, and yeah.
So let's take a question from
Sure.
here. We'll just kind of go back and forth.
So one thing that you briefly mentioned in your algorithm is prioritization. So like, if there's like 2 planes in the queue, 2 domestic planes, and the third one in the queue is an international plane, then in some scenarios it would be more advantageous to allow the international plane to go first and
Yes.
allow the domestic plane to go.
Yeah.
So how do you go about figuring out that, like that algorithm? How do you go about figuring out?
That's an excellent question, and that's exactly right. So it turns out that in the air traffic system, one of the things that they will say in terms of fairness is first come, first serve. So that's how we do it. But one of the things that we did show when we showed at the end of this is show that really if you were optimizing on fuel burn, you should be holding, you should be doing things differently. So a lot of it is also presenting to the decision makers what the trade-offs are. But you're absolutely right. So telling them, and then part of it, as I said, as we go forward to other programs, helping policymakers understand what they should be optimizing over. Right? It can't be only this. You should also be considering other impacts. But it's a great question.
Maybe one more.
Do one and then move back, maybe. Yeah.
So you talked about this being in Logan. Is it any other airports, or are you trying to expand it to like the national thing?
So there is an FAA program which will go everywhere else. So with NASA, they are currently having field tests at Charlotte. So part of what we do is we support essentially tell them what is likely to happen, right? Because now that we have the models, we can say, okay, here's how you implement. So it is expected to become nationwide. Yeah. Sorry. Yes. Yeah.
For air trafficking algorithms and scheduling, have you ever taken into account the statistics of past failures by based on type of plane, like a Boeing?
Not in this. So when you're thinking about the system-wide thing, the maintenance issues are pretty minor. One thing I didn't talk about, but we work on, is a lot of statistical modeling of engine performance. And there, absolutely, we look at different aircraft things. So certainly the methodologies can be looked at other factors, but the focus has primarily been on looking at performance rather than failure things, right? But it's certainly the methodology extends. Yeah, absolutely.
Okay, maybe one
One
quick
more,
question,
and then I'll.
and then we run out.
Yeah.
Yeah.
I just want to know, how did you become interested in this specific field?
I travel a lot. No, so for me, so my background, I started off, I did my undergrad in aerospace engineering, and I wanted to do aircraft design. So I went in as I started grad school as a fluid mechanics person. I then really liked control and optimization. So it's always been from liking the physics and the math of it. And then I realized that there were really challenging abstractions, right? So how do you merge this thing between the abstractions and the operation side of things, where it's nice to see things, so to work towards building things that can actually get deployed, that you can convince people are the right models. And so everybody moves around, but I think for me it was more that I really liked the idea of transportation being something that impacts all of us. So.
Okay, let's thank Professor.
I'm here, so I'm happy to answer any questions. Yeah.